Okay, I did get word from my math department that my webcam should be here soon. And that's definitely going to improve the quality of the video. I watched the video the other night, and you can kind of sort of see what's on the board. But hopefully with the webcam, it'll be much better. Oh, and by the way, Julie, wasn't that you who sent me the email and who said, I thought I told you? Was there a previous email that I don't remember?
No, I was half asleep.
Oh, okay.
Sample, if you don't mind, but
oh yeah, no, I don't.
I came back, I looked at it later, I'm like, that's confusing.
Yeah, it was. I was like, what did I miss from the conversation? Anyway, that's totally fine.
No, it was like, let's see, pizza finally finished delivering at 10 o'clock, and I was still doing homework. And the guy I was talking to, he was having a lot of trouble with his business calculus class over at MCC. He said that a lot of his fellow students were. I'm like, oh, what is this professor? He goes, he has a big white light on it, but if you just listen to what he's saying, it makes sense.
Yeah, and there's no more bright white. Well, the early videos, yes. Yeah. This video, no. All right, folks. Well, let's go ahead and review. We're going to do a global review of what we've been looking at. So how do you find the x-intercepts of a function? How do you find the max and min of a function? And how do you find the point of inflection of a function? Let's see how all of this fits together. So let's just say, again, that we have this function, which is an upside-down parabola. That's kind of the classic starter function. Why would we in a business calculus class really like this function? An upside-down parabola. Any thoughts on why this is used the most in the textbook?
Shows how things go up and down.
Absolutely, it shows how things go up and down. And one thing in particular that goes up and down is cost. When you're a business and you're looking at the cost of all of your supplies, you know, if you just buy, you know, some supplies, you have a certain cost. And as you buy, wait a minute, am I thinking about this the right way? Yeah, cost goes up and then cost goes down. Because essentially you can get a discount the more you buy. Like if you're buying in bulk. Or do I have this backwards? I might have this backwards, folks. Definitely, maybe cost is a right side up parabola. Would that make more sense? It's one or the other. Perhaps cost goes like this. That you start buying supplies, but then as you buy more, you get a discount. But eventually, there comes a point where you're buying so many supplies that you're literally depleting the resource market, that it starts costing more money again. Like buying wood, for instance. If you just buy a little bit of wood, you have to pay a certain price. But then as you buy more and more wood in bulk, you're getting a discount. But eventually, the forests of planet Earth start running out, and there's not as much wood to buy, and then the cost goes up because it's a scarce resource. So in any case, you could have a right side up parabola representing cost. But then your profit, here we go, your profit could be an upside down parabola. Because essentially, as you start selling more and more goods, you're making more profit. But there comes a point of diminishing return where the more you sell, you're not actually making as much profit anymore. And why not? What's too much? You're making too much of a product? Oh, well, I suppose that could be it. But also because your cost is going up. Eventually, your cost is going up so high that you can't make as much money in the long run. Okay, so we have these two classic curves that we use quite a bit in business because costs will go down and up and profit will go up and then down. And so let's just go ahead and pretend that we're working with, say, negative x squared plus 4x. That'll be my function that we're looking at. So first of all, how do you find the x-intercepts of a function? Like just the regular function. We're not even talking about the derivative yet. Just how would you find the two x-intercepts, those 2 points that kind of mark off 0? Because this is the only place where the profit makes, or the function makes sense. We wouldn't look down here, for instance, or down here. So how do you find the x-intercepts?
And the y equals 0?
Yeah, you would set y equals 0. You would set this equal to 0 because, of course, that's what this means. This is a coordinate x comma 0, and this is a different coordinate x comma 0, or I can call that x1 and x2. And so you set y equal to 0. So if I take my function and set it equal to 0, how do I solve for x? How do you just solve a normal quadratic? This is old school material. How do you solve a quadratic?
Either times -1 or using a quadratic.
You could just factor it, right? You could always just factor it. So I could take out, say, an x, or better yet, I'll take out a negative x, and that leaves behind x minus 4. And now this is a factored expression, and I can set both of those equal to 0. So factoring is one way. What's another way? Maybe the classic way of solving a quadratic. You write it in standard form, ax squared plus bx plus c, and then you use the quadratic formula. So you can either factor, factoring works, or you could use the quadratic formula. And I would say that's probably the two major ways that you or any of us would want to solve a quadratic. You can either factor it or you could use the quadratic formula. You could complete the square too if you wanted to, but that would be it. Okay, so the main idea here is that if you did want to solve for the x-intercept, you set the function equal to 0. And this is the main. This is something that we do over and over again. You either set the function equal to 0, and so that's one main idea here. What do you find if you set the function equal to 0? You're finding the x-intercepts. That's what you find if you set the function equal to 0. Meaning, you're saying that the y value is 0, which puts you on the x-axis, and therefore it's the x-intercept. All right, so that was the first question. How do you find the x-intercepts of a function? Second, how do you find the max and min of a function? Let's say you actually wanted to find the max, or better yet, how do you find the critical points? What do you do that? You take the derivative, and then what? So here's my f prime of x, which in this case is negative 2x plus 4. And once I find my derivative, this is going to tell me where the function has a positive slope, a 0 slope, and a negative slope, depending on what value you put in for x. So how do you find the critical value? You set that equal to 0. So then you set this equal to 0, the derivative equal to 0.
You do what you just did on top.
Yeah, I do what I just did on top. Literally, it's the same methodology. Now I'm just taking the derivative and setting it equal to 0. And then that gives me x equals 2, and that would be where my critical point is. Now, when I set the derivative equal to 0, do I know that I'm finding a max or a min? I don't know which yet. I don't actually know which. I happen to know now that it's a maximum because I'm looking at the graph. But if all I did was just set the derivative equal to 0 and then solve, all I know is that x equals 2 is a critical point. That's it. That's all I know is that it's a critical point. So it could be a max, it could be a min, but I don't know yet unless I'm looking at the graph. So if setting the function equal to 0 tells me the x-intercepts, setting the derivative equal to 0 tells me the critical points. And the critical points, there's a few different types. It could be a max, it could be a min, or, remember those 4 possibilities? It could be a max, it could be a min, or it could be a
Flat.
A what?
Like flat.
Oh yeah, it could just be flat, because, oh, I should write flat. It could just be a flat constant graph because the slope is 0. Or there was a 4th possibility.
The cubic.
Yeah, a cubic. Very good. It just is a cubic. And I suppose I'll call that a leveling off. Leveling off. So it means it didn't actually do a maximum or a minimum, but it just temporarily leveled off flat before it continued on its way. So that's what you're finding when you set the derivative equal to 0, is you're finding critical points. Now, there was actually, the definition of critical point from last time was more than just setting the derivative equal to 0. What else did they say? Critical points are any time the derivative is 0 or undefined. So, undefined. Now that's interesting. When the first derivative is 0, it could be any of these, but when it's undefined, what could it be? If the first derivative is undefined, what does that mean is happening? It could be vertical, yeah, it could be vertical. So it could be infinite slope. What else could it be? The function could temporarily go vertical, right? So that'd be like a sideways cubic. Or what else could be happening when the slope is undefined? And we were calling an undefined slope, like a point that's undefined as a teeter-totter point, meaning there is no well-defined slope there. It's undefined. And so it could be a cusp. Yeah. Wow, that's a whole lot of exceptions, isn't it? That's a whole lot of different possibilities when the slope is either 0 or undefined. It could be a vertical point, it could be a cusp, it could be any of those things. So when we in general set the first derivative equal to 0, we're finding one of those things, but we don't know what. And when we set the first derivative and find out if it's ever undefined, we're finding one of these things, but we don't know what. So how then, without looking at the graph, which would make it so obvious, just look at the graph. without looking at the graph, how could we figure out if it's a max, min, flat, or a leveling off point? What additional step would you do? Take the second derivative. Yeah, that's when you would take the second derivative. And so how do you find the point of inflection of a function? Or in general, how do you use the second derivative? So by using the second derivative, and now in this example, my second derivative would be simply -2. Well, this is telling me that my concavity is always negative. That means this function is always concave down. And that would tell me right away whether my critical point was representing a max, min, a flat, or a leveling off. So since this second derivative is negative, could it be a maximum? Yeah, most likely that is what it is. Could it be a minimum? No, that's impossible. Because it's concave down, it can't possibly be a minimum. Could it be flat? No, because it's concave down. You know, the concavity thing, I like to think of a metal bar, and like a strong person would either bend it down or bend it up. I don't know. Have any of you taken a metal bar ever and bent it like that? You know what I'm talking about, right, though? Like a strong person? I was going to say a strong man, but that sounds sexist these days. So it could be a strong woman or a strong man. But concavity-wise, since this concavity is negative, that means it's definitely bent, okay? So it cannot be flat. Could it be this? Hey there, Rose. Could it be the leveling off point? Because on the leveling off point, what concavity is to the left? Concave down. What's the concavity to the right? Concave up. What's the concavity at the point? What is it? Right there where it changes from negative to positive, it must be an inflection point. The concavity is 0. And is our concavity 0? No, so it couldn't be that either. So using the second derivative, we just narrowed down that this particular point, if we weren't looking at a graph, we would know it has to be a maximum because the concavity was negative. And so when we look at each of these for a concavity test, this concavity must be negative, this concavity must be positive, this concavity must be 0, this concavity must be 0. What about this? Is there concavity there? No. Using the strong person test, there's no concavity here. That'd be a concavity of 0. What would this concavity be? Also 0, because it's going from concave up to concave down, it's going from plus to minus, and therefore that concavity right there is 0. And then what about a cusp? What's the concavity at a cusp? Undefined. It's undefined concavity. Because, again, there's no derivative at that point. It's a teeter-totter point. And because there's no derivative, you can't have a second derivative. Does that make sense? If you can't even take the first derivative, you can't possibly take the second derivative. Right? If you can't take the first derivative, you can't take the second derivative. And so this concavity is undefined. Wow, this is really interesting. This is a really nice summary of all the knowledge that we've been learning. That just from taking the first derivative and either setting it equal to 0 or undefined, you get all these different possibilities. And then by taking the second derivative and applying the concavity, you can really start to narrow down what you've got. Right? Yeah, because all of these were a first derivative equaling 0, and then all of these were a first derivative being undefined. So does this, in fact, completely categorize what's happening? Like with just knowing that the first derivative is 0 and knowing the concavity, can you distinguish between all 4 of these? Like, if the first derivative is 0, a negative concavity, I know it's a maximum. A positive concavity, I know it's a minimum. But if I got 0 concavity, would I be able to distinguish between these two? I wouldn't, actually. I wouldn't be able to distinguish these two. If all I knew was that the first derivative is 0 and the second derivative is 0, I would still be stuck saying, well, is it flat or is it a leveling off point? I don't know. How do you suppose you'd find that out? Graph it. Yeah, I mean, always just graph it. Do you suppose maybe you might be able to do a third derivative test? Maybe if you did a third derivative test, you'd be able to tell the difference between something that's truly flat versus something that's just leveling off. I don't know. We haven't gotten that far yet. All right, well, folks, so what are we finding when we set the second derivative equal to 0? When you set the second derivative equal to 0, you're just finding an inflection point. And I hope that now you see that the inflection point isn't even really all that interesting. An inflection point, where do we even have an inflection point up here? That one is an inflection point. And any others? That one is an inflection point. So it's not just setting the second derivative equal to 0 that's really interesting. It's just knowing if the concavity is negative or positive or 0, because that helps you distinguish between these possibilities. Okay, so folks, those are our 3 tests. In general, we take the function, derivative, and second derivative and set it equal to? Yeah, that's just the thing. It seems to be that that's just always what we're doing in mathematics, is taking some function and setting it equal to 0. Isn't that kind of interesting and strange? Psychologically, I don't know what that says about us as a culture, that we're always equating something with nothing. Isn't that a little strange philosophically? We're always saying, hey, take that and set it equal to nothing. I think that's kind of strange. All right, well, today, folks, we're going to look at section 2.8. Next week, when you come back, we'll do 2.9 and 2.10, and then we get to take a test. And I will unfortunately not be here for the test, but I will, as I mentioned before, I'll give you a practice test. I will write all the answers to the practice test and post it online so that you can review all of my solutions. And then I might even try to make some sort of video or something. But no matter what, the sub will do a review day with you, and then you'll take the test.
Where are you going? Like, I know it's really difficult here.
Well, I will tell you where I'm going. But I just want you all to know that A, I feel guilty about not being here. B, if I could cancel the trip, I would. Sorry, wife. And just in case she ever watches this. And we planned the trip before I knew I was getting a job at Gateway. I was still a high school teacher. And as a high school teacher, we had a 2-week fall break. And so my vacation was scheduled right during the fall break. I wasn't going to miss any school at all because I would prefer not to miss school. We're going to Maui for a week with our daughter. I know, it's terrible. It's terrible. I know. That's why I feel so bad about it. I mean, obviously, I'd rather be here with you. I think you guys actually believe me when I say that. I bet you do actually believe me. All right. Maybe that was all already a joke to make you laugh, but I do have another joke for you. This is more of a riddle. What does a dog do that a human steps into? Any immediate guesses? I mean, something should spring to mind immediately. What does a dog do that a human steps into? Pants! You were all thinking poop, weren't you? At least that's how the riddle's supposed to work. All right, so here we go, folks. We're going to look at section 2.8, and I think we can just dive in because we have all the theory that we need in order to understand how this material works. We're looking at the function, the first derivative, and the second derivative, and that's telling us everything we need to know. You see everything? Come over here.
I'm going to finish that 2.7.
Oh, did we not finish 2.7?
No.
Oh, you're right. Do you want to go back? I think I did. I had said we would do one more problem. What's that? Number 3? Okay, that's fine by me.
We did number 3.
Number 7.
Yeah, I think it was number 7. You're right, Mom.
I don't know how we got like fun.
Here. Where?
It's not on you have to like this one. But I know only made one.
We didn't do number 3?
Yeah, we didn't.
Oh, okay. All right, folks. Well, let's just go back a click and look at number 3. I do want to make sure that we finish it. So the function is this cubic, and so we need to find, apparently there's a minimum and a maximum. And that makes sense because as a cubic, when we take the first derivative, we now have a quadratic, negative 6x squared plus 42x minus 36. And so you take the first derivative and set it equal to 0. So I'm going to set that equal to 0. And we immediately factored out a negative 6. So I divide negative 6 out of everything. And that gave us x squared minus 7x plus 6. And then we factored that into x minus 6, x minus 1. And therefore, the two values of x are x minus 6 equals 0 or x minus 1 equals 0. And so x equals 6 and x equals 1. So all we know for sure now is that those are our critical values. They are our critical values. So it could be a max, it could be a min, it could be a changeover point, it could be flat. So what we need to do now is what? In order to distinguish between them, you find the second derivative. So now I find the second derivative, which is negative 12x plus 42. Oh, yeah, we did do this. I totally remember this now. So the second derivative, if I plug in 6, then that's negative 12 times 6 plus 42, which is what? Negative 72 plus 42, which is negative 30. So Mong, that tells us that at the value 6, the concavity is negative. And if the concavity is negative, what is it, a max or a min? The max, because it's at the top. Yeah. So my point x equals 6 is a maximum. And I only know that by looking at the second derivative, the fact that the second derivative was negative. We don't even have to interpret the 30. We don't have to look at that and say, is that down 30 right 1? We're not even interpreting it. We're just saying, oh, it's negative. So that means the strong person has bent the graph down and it's concave down. Whereas now if I plug in the value number 1 into the second derivative, then that's negative 12 times 1 plus 42. And that's negative 12 plus 42, which is 30. And all that matters is the fact that the 30 is positive. That means now that it's concave up. So Mong, is that a min or a max? A minimum. Yeah. And that's it. Thank you, Mong. That was a really good way to start class.
So you put it on with value, it's gonna be, the first one is going to be minus value.
The first one, the function has a local minimum at x equals 1. Oh, with the value. So
Yeah,
now you
with
just
the
plug
value.
1 into it. So that's where the minimum is, and then you plug it in and calculate it. So that'd be negative 2, 1. Oh, you're right, Mom. We did not do this.
Yeah.
21, 1 squared minus 36, 1 plus 1. And so that's negative 2 plus 21 minus 36 plus 1. So that's 19 minus 36, which is 7. Negative 17 plus 1 is negative 16. So the value of the minimum is at negative 16. Yeah. Boy, Mom, thank you so much for asking this question. This is literally, folks, we're using all 3 functions, aren't we? We use the first derivative to find the critical points. We use the second derivative to find out if they were concave up or down, therefore min or max. And then we use the function itself. Would that be the 0th derivative? It's not the first derivative, it's not the second derivative, the 0th derivative? No, it's just the function. We use the function itself to actually find out the y coordinate at that point. Boy, what a good problem. So Mom, the maximum is at x equals 6, and what's the actual value there? Ugh, you'd have to plug that in. Negative 2, 6 cubed plus 21, 6 squared minus 36 times 6 plus 1. And then you calculate that, and that's your actual value. Mom, does that make sense?
Yeah.
Yeah, really good question. Boy, this is a really good question, folks. This is the type of question that if you were on a long overnight flight, say to Maui, and you didn't have anything else to do, you could just sit down and solve like 10 of these in a row. You know what I'm saying? That'd be very entertaining on an airplane. Okay. Yeah, really nice. I would really call that just the perfect problem because you have to use the first, second, and 0th derivative. Well, the function. Yeah, what a good problem. Okay, so we said we'd do 3 and which other one? 7? Actually, 7 is just like it. Oh, that's 6. 7 is not just like it. Well, it kind of is. It's just on a particular domain. It says, just look at the function between negative 3 and 2.
We did number 5.
Yeah, I think we kind of, was it 5 that we said we were going to look at?
And that was it.
Oh, yeah, 5. So 5 is just like the one Mom just asked about, which was what, 3?
We did 5.
Oh, we did 5.
Yeah, we just didn't do the.
We just didn't plug it back in. Okay, okay. But so now you all know that you just plug it back into the regular function, and that tells you the actual value. Okay, well, great. So moving on then to section 2.8, everybody grab one from the counter. And by the way, Thomas, I finally did find that I had some 2.6s, but you have one now. Right? So Mom, I'm going to give you back your extra 2.6. Does anyone else want an extra 2.6? You're going to go there? Well, you never had one? No. Oh, no. Here you go. Anyone else want another one? You can do it twice. No? Okay. So looking at section 2.8, this whole chapter was called curve sketching. Isn't that what they said? It's called curve sketching. They want you, now this might be a little counterintuitive, they want you to develop the ability to figure out what the graph looks like without using a graphing calculator. All right, so this is the weird thing. All class long, I've been making this long joke about what should you do? Graph it. What should you do? Graph it. What should you do? Graph it. And yet this chapter says, pretend you don't have a graphing calculator. Because they want you just to use the mechanics of the calculus to figure this out on your own, as if you're on a desert island and you don't have any technology. A desert island, like Maui. No, totally good. So that's all they're asking us to do. So let's just go ahead and take a look. It says sketch the graph. So again, not using a graphing calculator, but sketch it yourself. It is kind of fun. So starting off with number 1, I think we can generally assume that we're in the first quadrant. That's why I always make my graph like this. I don't draw a full coordinate axis. And they say sketch this graph. So take a look. They're giving us, well, the function, the first derivative, and then whether or not it's a maximum or a minimum. So how do you read f of 1 equals 3? It's just the coordinate 1, 3. So the input is 1, the output is 3. That means the input is 1, the output is 3. So I have a coordinate right there at 1, 3. And they're telling me that the first derivative, that is the slope, at 1 is 0. So now I know that it's actually flat right there. But since we know that the first derivative is 0, all we really know is that it's a critical point. And I should really have kept these up on the graph, or on my whiteboard. So if f prime of x equals 0, all we know is that it's a critical point. So it could be a max, it could be a min, it could be flat, and it could be a changeover. Whereas if f of x equals undefined, then in that case it could be what again? Vertical. It could be a vertical changeover, or it could be a cusp of some sort, a teeter-totter point. I've actually never heard anyone ever call it that before, but I'm in love with the idea, a teeter-totter point. It sounds so fun. So do we know which of those 4 it is yet? Not yet, but if we just keep reading, it says the 0.13 is a local maximum. So it must be that. Then that's it. We just put this information together. It says sketch the graph of a continuous function. Well, that's all the information they gave us. And I'm assuming that they only want a single local maximum. So what could the rest of the graph look like? It could just be an upside down parabola, right, for all we know. It could just be the parabola, f of x equals negative x minus 1 squared plus 3. And there, that actually goes all the way back to chapter 1. Is that the right way to make a parabola that's upside down has been shifted right 1 up 3? Yeah. So there we go. We went one step beyond what they're asking. Not only did I sketch a graph, but I even gave the function for it. And at that point, I could even confirm that the first derivative is 0. Wait. Oh, yeah, that the first derivative is 0 at 1. So if I took the derivative, it'd be negative 2x minus 1. And if I plug 1 into that, negative 2 times 1 minus 1, that really is 0. Anyway, you don't have to keep going. You know, I like to run with the problem, but we're done. So you can totally finish B and C. Let's move on to graphs 2, 3, and 4. So in problems 2 through 4, sketch the graph of the derivative. Now this is very fun. They want us to sketch the derivative right on top of the graph that's already there. So what do you suppose would be the easiest point to graph of the derivative? Yeah, where the max or min is. That's always the easiest. So like for instance right here, I have a minimum, which means the derivative value is 0, which means I know that the point on the graph is right there. So then what else? Here the derivative is negative. That means my function, my derivative function must be negative. So I'm just going to put it down here somewhere. That way it all has negative values. It doesn't even matter how I draw it. It just has to be negative because the slope there is negative. And then here my derivative values are all positive. So I just need to make sure that I give my derivative positive values. Now mine's a little wavy. Did it have to be wavy? No. The fact is I don't know much about this function. So it could be anything. And for all I know, it could actually just be a straight line. That would be a perfectly acceptable first derivative. And again, you just have to go back and check yourself. This is the derivative, and therefore it's telling me the slope. Is the slope of my graph here really 0? Yes. Is the slope of my graph here really negative? Yes. Is the slope of my graph here really positive? Yes. Questions about that?
Can you do one more?
Yeah, because honestly, these do hurt the brain a little bit. Because what you have to constantly tell yourself is this derivative function, because the value is positive, that's telling me that the slope of my original graph is positive, which it is. And because this value is negative, meaning the y value is negative, that means that the slope of my function must be negative, which it is. So the value, that is the y coordinates of this derivative function, is telling me the slope of my actual function. So to do another one, Carmen, you choose. Which one?
Whatever. How about number 4?
Number 4. Okay, sounds good. You probably chose number 4 because it has cusps and teeter-totter points. Yeah, that does make it tricky. What is the slope right there? It's undefined. Now, to be undefined, that could either be an asymptote or it could be a hole. We don't know. So let's leave that alone for a second and just focus on this. What's the slope right here? Positive, and we can go ahead and take a guess, everybody. What would you say? In terms of a numerical value.
1.
Yeah, would you say up 1, right 1, up 1, right 1, up 1, right 1? That seems reasonable. So right now, my derivative has a value. My m is up 1, right 1, and so therefore the derivative value will be 1, at 1. So going right up until that point, the derivative is 1. I don't know what happens right there, so temporarily I'm going to put a hole, because I don't know what the value of the derivative is there. But then we get to this part of the graph. What's the slope now? Negative, obviously, but let's give it a value. Should it be down 1, right 1, down 1, right 1, down 1, right 1? That seems reasonable. So now the value of my derivative function is at -1. So extend your graph down to -1. And then now starting there, it's going to be at -1 all the way to here. And again, I don't know what the value of the slope is right there because it's a cusp, so I'll put a hole. Because I'm not defining that point. Nate?
Wait, didn't we just say that would be -1/2?
Oh, I didn't.
Oh, I thought you did.
I mean, if I did, I'm not aware of it.
It should be.
You think so? Oh, it might not actually. Oh, you're right. That totally is it, isn't it? Oh, and I said that? I don't think I said that. I think you thought it correctly.
Yeah.
And you inserted it into my words. And that's fine. You're right. That is down 1, right 2, isn't it, folks?
Yeah.
So it's down 1, right 2. Did I get this first slope right? Yeah. Up 1, right 1? Yeah, okay. So I actually have to redraw my graph. It's at -1/2. So if that's -1, that's -1/2. And then so starting right there, which again is a hole, we go all the way over here and put another hole there. Thanks, Nate. And then should we go back to a positive slope of 1/1? So now again, the slope is up 1, right 1. And so we're going to go back and put our derivative function back up here, starting here at here. Does that make sense? Always once you draw it, you should go back and just ask yourself, well, is my slope of my original function really -1/2 right here? And you look up and you're like, oh yeah, the slope really is -1/2. And then you go here and you say, well, is the slope of my function really up 1, right 1? Is it really 1? And you say, oh yeah, the slope really is 1. And then here you say, is the slope of my original function really 1? And you, oh yeah, it is.
So because it has like a teeter-totter point, it's gonna be like that. But if it were like an actual curve.
Yeah, now that would be interesting, folks. What would suddenly change with our graph if instead of being a teeter-totter point, it actually did smoothly and suddenly curve to the next point?
That's when we would use the min and maxes for our zeros, right?
Yeah, and you know what would be exciting? What would happen is, instead of being a hole right there, the graph would simply really quickly go, right? Because it would have to reach a 0 value at the top of the maximum. So it would have to just cut down really fast, go through the 0 point, and then here again it would go, and go like that. Now, would it actually be vertical? No, it wouldn't have gone vertical, but it would have had to transition very quickly to come down here, go through 0, and hit the other thing. Yeah, that's what it would look like. Okay, well, this is all curve sketching. Like I said, we're just trying to imagine what these graphs look like. In the next view, it says the graph of a helicopter. The height of a helicopter is shown. Sketch the graph of the upward velocity of the helicopter. Oh, this is interesting. So we have been talking about distance, velocity, and acceleration. What's the relationship between those? If your function is telling you height, what would your first derivative tell you? Velocity of the helicopter. If the original function is telling you height, or position, or distance, then the first derivative is velocity, and the second derivative is acceleration, and the third derivative is sure. We probably won't be using that here, but it's fun to include it. All right, so this is the first, this is the original function, f of x. And what do they want us to do? Sketch the graph of the upward velocity of the helicopter. That's a little confusing. What do they mean just the upward velocity of the helicopter? They don't want to graph it if it's downward velocity? The height of the helicopter is going up and then going down. So the helicopter had upward velocity and then downward velocity. Right? So from here to, first of all, what's the helicopter's velocity at the top? 0. So we can go ahead and put 0 velocity right here. That's where the helicopter's velocity is 0. Whereas as the helicopter is going up, what is its velocity? As the helicopter is going up, its velocity is positive going up. So we would say that the velocity must be doing something like this. That the velocity is positive, but it's getting slower and slower and slower until the velocity stops. And then what happens? The velocity, or the helicopter, comes down. And so that means its velocity is negative. The velocity is negative because it's going in a downward direction. That's really what they meant here. They want to sketch the upward velocity of the helicopter. That means that we're defining velocity to be positive if you're going up, and your velocity is negative if you're going down. So now that the helicopter is coming down, it has negative velocity. And notice that at first, the slope is very steep. Right? So that means that its downward velocity is incredibly fast. But then later on, its downward velocity levels off. And so he's getting less and less fast towards the end. So it looks something like that. Now, honestly, just curving, sketching it like that, maybe that's not even the best choice. Maybe the best choice is to talk about steepness. Like right here, that's quite steep. So I would give a velocity value quite high. And here it's still quite steep, so I'd give a high velocity value. But here it's leveling off, and so I'd give a lower velocity value. And by plotting those points, and then I connect them. So likewise, right here it's very steep, so I'd give it a very large negative value. Here it's still quite steep, but not as much. And here it's leveling off, and then here it's barely any velocity at all. So then I would connect these dots, and that would tell me what to do. Probably better to take a whole bunch of individual snapshot points of steepness and then connect them. Okay, is that all? I mean, is that okay if we move on from there and you can try the rest? Carmen?
Mm-hmm.
What do you think about that? Huh? Thank you, Carmen, for volunteering to do this next problem with the group. Carmen, what's the velocity up here? 0, right? Its velocity, because it's just hovering, right? Isn't that what the helicopter is doing? It's just hovering, probably looking at traffic or an accident or who knows what. It's just hovering there. So what is his velocity right now? I would say here it's 0, so I put 0 velocity. Here it's 0, so I put 0 velocity. Here it's 0, so I put 0 velocity. Here it's 0, I put 0 velocity. So all those points are going to be 0. But what's my slope right now?
Positive.
Positive. So because it's positive, right here in that vertical plane, I'm going to give a positive value of velocity. And what's my slope here?
Still.
Positive. So in that same vertical line, I'm going to give a positive value. What's my slope here?
Still.
Positive. So in that vertical line right there, I'm going to put a positive value. So it looks like the velocity of the helicopter was something like this. It was going very fast, to get up in altitude, and then it slowed down and it stopped and just hovered for a while. And then what?
Go up.
Now what's its slope?
Oh, go down.
It's a negative slope, so it's going to have a large negative value of velocity. And here again, negative slope, so I drop down in the same vertical line and I put a negative value. And here he's starting to level off, so it's not as negative, so I put a value here, and this demonstrates his negative velocity.
What did you do about that?
What?
What did you do?
Because it looked like he was leveling off. Doesn't it kind of look like he's leveling off a little bit? The slope does change. It's not as vertical towards the end. So he was starting to level off. Yeah, and in fact, humorously, folks, I would take a guess that the helicopter just crashed. Look how quickly it came down and hit the ground. You know, a real helicopter, I think, would have came down and hovered just off the ground and slowly touched the ground, don't you think? Because if a helicopter did what this graph is showing, the helicopter just came down and went, poof. That would be very unfortunate. Was that better, Carmen?
Mm-hmm.
Okay.
Thank you.
I think it's important that you go point by point by point. Don't just try to curve, sketch something in. You want to go point by point. Okay, well, the next couple of questions are still more of the same. They're just asking you to visualize what's happening in these graphs. So number 8 is over here for me. It says in the graphs to the right, match the graphs of the functions with the graph of the derivative. Well, this is fun. There we go. So graph A, B, and C, the derivative is either P, Q, or R. How will you identify which is which?
B and P.
You what do you what?
B and P.
You think B and P?
Yeah.
Why is that?
B.
Tell me what led you to that conclusion.
Well, like the min
The other min?
is at 0, so then you
Zero slope, so that's a 0 value.
and then the derivative or the slope is negative.
Yeah, over here the slope is negative, and these are negative values. And over here the slope is positive, and those are positive values.
Yeah.
Yeah, so for sure B and P go together. Yeah, that's absolutely right. And that was a really good analysis because you went basically point by point. Rose considered a point in the middle, a point to the left, and a point to the right. And doing those 3 points, that gave her enough reason to believe it was P.
C and R.
Yeah, probably C and R go together. Now, I suppose even anybody who doesn't know calculus right now would probably say C and R look the same, and A and Q are both wiggly. Now, that's not a very sophisticated analysis, but somebody might say that. But how can we make that less sophisticated, more sophisticated? What do you notice about C's slope? It's always positive. Well, and R is always positive. R always has positive values. Q doesn't always have positive values. In fact, Q hits 0 twice, which means there's 2 maxes or mins. So definitely C goes with R because the slope is always positive and the value of the derivative of R is always positive. Whereas I think that was the giveaway, that this derivative is 0 twice. And anytime the first derivative is 0, that means you have a critical point, which is a max or a min, and there's your max and there's your min. Okay. Number 9 is similar, so I'd like to leave that for you all to do on your own. Okay. Finally, these questions, it says use information from the derivatives of each function to help you graph the function. Find all local max and mins of each function. This is really exciting. This is really the fun of knowing calculus, if I can convince you of that, is that you can make a pretty good graph without using a graphing calculator. Now again, right now in modern society, you'd say, why would I ever do that? Why would I ever do this? Because obviously, if it was for my job, I'd use a graphing calculator. I'd want to be correct. And we have so much technology, I would just use a graphing calculator. So I could just plot these into the graphing calculator. But then you're missing out on realizing that you actually know enough math that you are a graphing calculator. You are a graphing calculator. So let's do number 10 together. Which one should we do? Just a couple of them. That's a cubic, that's a cubic. I'm not going to do 11 with you. That's a quartic, so maybe we'll do 12. And then this is a rational function, and that's a rational function.
We do 1 of 12 and 13 and 14.
Well, both of them?
Or 1, either.
Well, yeah, let's definitely do one of them. They're pretty different. You know, because this one, the variable is only in the denominator. And here we have variables in the top and bottom, although if you simplify that, that's x squared over x plus 3 over x, which is really x plus 3 over x. So what function are we really interested in, this one or this one?
Just do both.
Or just do both? Well, we'll consider that. Okay, now for number 10, we already have a pretty good idea because it's a cubic. So what essentially is our graph going to look like? That. And at the very least, we have a changeover point, so there should be at least one critical point. No matter what, there's got to be at least one changeover point. But chances are that there could be more than one changeover point if it wiggles, in which case we could actually have a max and a min. So we don't know which is which yet. The graph is going to end up looking like one of these. So, of course, see, in pre-calculus, before you ever knew calculus, you could just do a table of values. If you just went ahead and plugged in all sorts of values into the function and you got a whole bunch of outputs, you would just take a graph and you would just plot a whole bunch of points and that would be your graph, right? That's how you would have done it before you took calculus. You would just make a large table of values, plot a whole bunch of points, and then say, oh, that's my graph. And in fact, is that how a graphing calculator does it? That's probably how a graphing calculator does it. It just plots tons of values and puts tons of pixels on the screen, and that's what we look at on a Desmos, and it looks like a graph, but it's really just a whole bunch of pixels because the graphing calculator did that process. So ironically, a graphing calculator is doing what? A table of values. That's all a graphing calculator is doing. It's plotting millions of tables of values in a table, and that becomes the pixels of the graph. But we're going to do something a little more sophisticated. We'll use calculus. So we start with what? The first derivative. Yeah. So that would be what? 3x squared minus 6x minus 9. And we immediately take the first derivative and set it equal to 0. And the nice thing is we can now go ahead and do what? We can take out a 3. So we divided 3 out of everything. And we get x squared minus 3x, sorry, minus 2x minus 3. And then what can we do with that? We can factor it. So that's really, what, x minus 3, x plus 1? Did I do that correctly? Yeah, minus 3 plus 1. And so that tells us that our two critical values are 3 and negative 1. They are critical values. And again, referencing my little cheat sheet over here, a critical value could be any of these 4 things. So it could be a max, it could be a min, it could just be flat, and it could be a changeover point. At this point, we don't know which is which because we haven't done our concavity test. Here the concavity would be negative, here the concavity is positive, here the concavity is 0, and here the concavity is 0. So hopefully when we plug those values in, it's either positive or negative because then we know which is which. If it turns out to be 0, we wouldn't know which is which. All right, so then we go ahead and do the second derivative, which is 6x minus 6. By the way, can I do the second derivative of this function? Because that's much easier. Why not? But this is the function I use to get my critical values. Doesn't it represent the same graph? Why can't you use this one? Yeah, this is the, wait, this is the what? Yeah, this is not the slope of the original function, is it? It is no longer the slope of the original function. We could realize that by even doing one test value. The actual slope at, say, 0 should be 3 times 0 squared minus 6 times 0. It should be negative 9. The slope of the original function should be negative 9 at the point 0. Whereas if I plugged 0 into this function, that'd be 0 minus 3, and that's the wrong value. So no, I cannot use this function, even though it's simpler. You might be tempted to use this one. That's no longer the derivative of the first function. You have to use the original derivative, not the one we simplified to solve for the x-intercepts. Okay, so we have our second derivative, and what are we going to plug in? 3 and negative 1? So if you plug in 3, 6 times 3 minus 6, 18 minus 6 is 12. That's positive. Therefore, 3 is a
Min.
Yeah, 3 is a min. And then negative 1, if I plug in negative 1, So 6 times negative 1 minus 6 is negative 12, therefore it's positive. Wait, sorry, therefore it's a negative concavity, and therefore it's a maximum. Yeah, so negative 1 is a max, 3 is a min. And that's it. Now, actually, there's one other thing we didn't do, and we didn't solve for the x-intercepts. How do we know where the graph goes through the x-intercepts? Do we know how to solve a cubic? We actually don't know how to solve a cubic. I mean, maybe if we could factor that thing, but I don't think that's what they're trying to get us to do right now, is to solve a cubic, because that's actually pretty hard. You'd have to use synthetic division, or you'd have to use the cubic formula. You all know the quadratic formula? You know there's a cubic formula? It's terrible. I mean, it's so much worse than the quadratic formula. So I'm thinking that we don't need to do that. So let's just go ahead and sketch the curve. What would it look like? We know that we have at 1, 2, 3, there should be a maximum. But where do I put it? And I know at negative 1, there's a minimum, but where do I put it? Where do I put these max and min values? This is the question Mon brought up at the very beginning of class. Now that I know that there's a minimum at 3, what do I do with the number 3? You have to plug it into the original function. So that'll be 3 cubed minus 3 squared minus 9 times 3 minus 5. So 3 cubed is 27, minus 27, minus 27, minus 5. 2 of the 27s cancel out, and that's negative 32. Well, that makes sense. My minimum is at negative 32. That's pretty far down. So at 3, I have a minimum at negative 32. That makes sense that the minimum should be far down. So I'm going to put a little minimum down there at negative 32. And then what? And then we have to plug in negative 1. So then negative 1 cubed minus 3 times negative 1 squared minus 9 times negative 1 minus 5. So that's negative 1 minus 3 plus 9 minus 5. Negative 4 plus 9 minus 5 is actually 0. What? Well, that's exciting. That means that the maximum value actually is right there. Wow. That was lucky, because now we do know one of the x-intercepts. And the rest of the curve, believe it or not, you just point your arrows out to infinity and you're done. That's curve sketching. It's just a rough type thing. Now notice, folks, that there are supposed to be 3 x-intercepts. How many x-intercepts do we have? Is this a contradiction? How do we explain this? There's supposed to be 3 x-intercepts. I'm just going to tell you a random fact. This is considered a bounce. The graph bounces off the x-intercept. That's considered a double root. It means that negative 1 is an x-intercept twice. So it's actually 1, 2, 3. So those are the 3 x-intercepts. Okay, well, that's it for the whole problem. I suppose at this point we really could factor the rest of that and find the other x-intercept, but we don't have to. Okay, doke?
We don't really need to do the actual, the second part.
The second part?
Yeah,
What's the second part?
yeah, like.
We definitely had to find the concavity to know if it was a max or a min.
Oh.
Yeah, we had to do all of this. We had to do the first derivative to find the critical values, the second derivative to determine if it was a max or a min, and then you had to plug it back into the original function to actually get the value of where that max and min actually was. Yeah, you definitely had to do all 3 parts, which kind of makes sense and brings all of calculus together, that you're using the function, the derivative, and the second derivative to solve a problem. So it's a very nice process that uses everything we know. And in what order? What order do we do? If you were to write down the steps, what are the steps? Step 1 is What's the first thing we do? Set the derivative equal to 0 to find the critical points. All right, what's step 2?
Second derivative and use the critical point.
Yeah, plug the critical points into the second derivative. So step 2 is plug into the second derivative. Right? So the first thing we did was set the first derivative equal to 0 in order to find the critical points. Then we plugged the critical points into the second derivative to figure out, to find if it was a max or a min. Then what did we do? What was step 3?
Call the value back.
Plug those same critical values into the first function to actually find out how high that max and the min actually was. So plug crit into f of x to see where to plot the max and the min. Isn't that funny? It seems that kind of out of order. First you deal with the first derivative, then you deal with the second derivative, then you go back to the original function. So let's follow those same 3 steps to do the next problem. What's our next problem? That's what, we'll do a quartic. Now what should a quartic look like? What should a quartic look like? Because it's an even power, so it's going to look like it'll just look like a parabola. The difference is it could have some wiggles. How many wiggles? Well, how many x-intercepts could there be? 4. So that means when we graph a quartic, you could theoretically have 1, 2, 3, 4 x-intercepts. So that's theoretically what our quartic could look like. It doesn't have to look like that. The wiggles could end up being completely below the x-axis, and we would only have 2 x-intercepts. The wiggles could end up, is it fair if I call this the letter W?
Yeah.
The letter W could bounce off the middle, and we would only have 3 x-intercepts. So you could have 4 x-intercepts, 3 x-intercepts, 2 x-intercepts. Could you have 1 x-intercept?
Yes.
How could you have 1 x-intercept?
To one side lower than 0.
The W bounces off one side and stays above the other. Oh my gosh. So a quartic could have 4 x-intercepts, 3 x-intercepts, 2 x-intercepts, or 1 x-intercept. Could have 0 x-intercepts. Of course, it is just floating up above. Right? But in all the ways that I just drew that, how many minimums are there? 2. Does it have to have 2? It could look like that. This could have been a changeover point. You know, the changeover point that we've been talking about could have looked like that. In which case, you'd only have 1 true minimum and 1 changeover point. How many inflection points could there be? Remember we did this theory just the other day? If you have a function that's x to the n, how many critical points could there be? Wasn't it n minus 2? N minus 2 what? Critical points or inflection points? I think it was inflection points. Isn't that what we discovered? Yeah, I think so. Yeah. There are n minus 2 inflection points. And so if there's 2 inflection points, sorry, since this is a 4 minus 2 is 2, if there's 2 inflection points, that means you'd have to change from positive to negative once, and then change from negative to positive twice. So in fact, yeah, we would expect to have 2, well actually 3 maybe, critical points. Okay, maybe I'm talking about this too much. I'm just exploring the ideas here. We're exploring how many, what the different ideas are. Okay, so should we just go ahead and do it? That makes sense. Let's just dive in. But now we have a little preview of what our graph could look like. So what do we do first? Now that we wrote our steps out. First we do the first derivative and set it equal to 0. So f of x is x to the 4th minus 8x squared plus 3. So f prime of x is 4x cubed minus 16x. And that's it. And what do we have to do with that? Set it equal to 0. This is pretty handy. What can we do with 4x cubed minus 16x? We can take it to 4x. So now we have 4x outside of x squared minus 4. Ooh, this is handy. What else can we do? Yeah, x minus 2x plus 2. That's a difference of squares. So now I have 4x times x minus 2 times x plus 2. And in fact, just to be handy, I'm going to separate the 4 from the x. And then you know what else I'm going to do? Just to write it in a particular way, I'm going to write x minus 0. Because what does each factor tell you? Each binomial factor tells you a... Yeah, well, it tells you an x-intercept. Yeah, it tells you an... Well, I'm sorry. It tells you a critical point. It helps you solve for 0. So since all of these are being multiplied together, I know that x minus 0 should equal 0. I know that x minus 2 should equal 0. And I know that x plus 2 should equal 0. So that tells me x is 0, x is 2, and x is negative 2. Those are my 3 critical points where the derivative is equal to 0. So we actually found 3 critical points.
That means they're concave.
What's that?
The critical points are concave. Yeah.
We don't know yet.
Okay.
Critical points could be
Yeah.
any of these.
Yeah.
Yeah, critical point could be concave down, concave up, flat, or a changeover point. So now that we're completely done with step number 1, we found all of our critical points. Now what do? We plug all those critical points into the second derivative. So our second derivative is what? 12x squared minus 16. So we get to plug all 3 of those values in to find out if they're positive or negative. So at 0, that would be negative 16. So that's concave down, so it's a maximum. At 2, 2 squared is 4. 4 times 12 is 48. 48 minus 16 is positive. What is it, 32? In any case, it's positive, and therefore it's concave up, which means it's a minimum. And then what about f of negative 2? Negative 2 squared is also 4. 4 times 12 is 48. 48 minus 16 is also positive. So that's also concave up, which means it's a minimum. Folks, you notice how I just did those calculations in my head? It's because you don't even have to be all that precise when you're doing a second derivative, right? Because you just need to know if the final answer is going to be negative or positive. So even if I had made some sort of really tiny error, like 4 times 12, if I said it was 40. Well, 40 minus 16 is still a positive number. That's all you really need out of the second derivative. I don't want to suggest that we can be sloppy, but I'm saying we're really just looking to see if the answer is positive or negative. Because now we know we have a max and a min and a min. Okay, so that's step 2. Plug all those back into the original. Unfortunately, the original is not that bad. It's a relatively short function. So f of 0 would be 0 to the 4th minus 8, 0 squared plus 3. So that's 0 minus 0 plus 3, which is 3. So I know that my first coordinate is 0, 3, which is a maximum. Look how I'm recording my results. I'm like starting a little list of information now. So I plugged in 0, it was 3. That means I have a coordinate 0, 3, and that's a maximum. And then I'm going to plug in 2. So that's 2 to the 4th minus 8, 2 squared plus 3. So 2 to the 4th is 2, 4, 8, 16. Minus 8 times 4 is 32 plus 3. That's negative 16 plus 3, which is negative 13. So my next point is 2, negative 13, and that was a minimum. And then we'll plug in the point f of negative 2, so negative 2 to the 4th, minus 8 times negative 2 squared, plus 3. And because it's an even function, squaring a negative 2 gives us the same result, right? So that's still 16 minus 32 plus 3, so it's still negative 13. So that last coordinate is negative 2, negative 13, which is also a minimum. This is interesting. Look at what we've done. We're pretending that we don't have a graphing calculator, and yet we just came up with this. This is really the gold of what we just came up with, right? We found 3 points on our graph, and we know that they're either maximums or minimums. And using this information alone, we will do our curve sketching, where we draw a graph and we say, well, at 0, 3, that's a maximum. And then at 2, negative 13, that's a minimum. And at negative 2, 13, that's a minimum. Look at my silly graph here, if you can. Oh, shoot, that might be too low. My computer might be away. Can everyone see my silly graph? That's all I really know, right? But from just that, I'm able to just, sketch in the rest, knowing that it should look like a wiggly W. So I go ahead and I just, well, can I use a different color? This really is interesting. I mean, it's almost artistic. It's almost some sort of strange puzzle where that's all you see, but from that your brain fills in the rest. So from that, can you see the rest of the graph? Yeah, it's really interesting. And it's very different from the graphing calculator approach, which simply does a table of values and plots millions of pixels and calls it a graph. We're simply finding the critical points and then filling in the rest like so. Whoops. Like so. And that's what your graph will look like. How do you feel about that? Anybody have any feelings or thoughts? Do you think, wow, you just filled up a whole whiteboard for something that your graphing calculator could have done for you in like 3 seconds? Maybe. I mean, that could be what you're feeling. If you do, I understand that. Well, 400 years ago, when Newton and Leibniz were coming up with this stuff, they didn't have a graphing calculator. All they had was tables of values. And so they would sit there and do tables of values and plot all these points painstakingly. So for them, coming up with this machinery to immediately know where their critical points were and knowing that they're maximums and minimums, I mean, that was advanced technology of the day. That was a big deal. Okay, well, we should take a break, and then we'll come back and do 13 and 14, and then that's it for the book, and then we'll look at the Math AS problems that you guys had for 2A. Wow, 2A is quite long. Okay, so everyone, let's take a break. So let's see, it's 11:08, come back in at 11:18.
I have a little bit lost from last class.
You what, Carmen?
I have a little bit lost from last class. Like, how do you know negative 16 is maximum? Like, why positive number is maximum?
Why is a negative number a maximum and why is a positive number a minimum? That's a good question. Because, by definition, Carmen, if the second derivative is a positive number, that means it's concave up. This is by definition concave up. A positive number means concave up. Whereas if your second derivative is negative, that means concave down, which looks like this. Now this kind of makes sense, right? Because if you were to graph a positive parabola, how do you graph a positive parabola?
Like that.
Yeah, like this. And how do you graph a negative parabola?
I got like that.
Yeah, like that. Okay, so if the second derivative is positive, it means it's looking like a concave up.
Okay.
And therefore, what happens right down here at the bottom?
That is middle.
That's a minimum. And if it's concave down, what happens up here at the top? A maximum. Yeah. Boy, Carmen, that's a really good question. That's very important that you know that. Very conceptual.
That's not yummy. I had Rice Krispies treat. Oh, okay. Really think of
Thank you.
Oh, you're welcome. Did that make sense?
Yes.
Okay, good. Oh, I just erased the steps. Silly me. All right, folks, it's 11:18. Let's keep going. In the interest of time, I really want to get to those Math AS questions. So I still want to guide you for what we're going to do, either 13 or 14. Why don't we just look at how to do the derivatives? Because that's really what you need to do, is you need the original function, the first derivative, the second derivative, and from there you're just plugging in values. So how would we take the derivative of number 13? Ah, yeah, how very interesting. It could be the quotient rule. I was actually thinking of something else. How else could you take this derivative, 2 over t squared plus 1? Rather than the quotient rule, that's probably the obvious way. You could also write it down as 2 t squared plus 1 to the negative 1. Could you do that? And then you could do the chain rule. So you can actually do it either way. Why don't we see which way is easier? If you do the quotient rule, you've got ho d high minus high d ho all over ho ho. Or using the chain rule, you've got negative 2 outside of t squared plus 1 to the negative 2 times the derivative of the inside, which is 2t. That's just the first step. You still have to clean it up. Should we get the same answer either way? Yeah, of course we should. So now this is negative 4t all over t squared plus 1 squared. Or this way, we have negative 4t over t squared plus 1 squared. Does anybody suddenly have a new preference for which way you'd rather do it? The chain rule or the quotient rule? Could you always take a quotient and turn it into a chain rule?
No.
What do you think? Can you take any fraction in the universe? Like, let's say it's just the general function f of x over g of x. Couldn't I just immediately rewrite that as f of x times g of x to the negative 1? And then it would be the product rule with the quotient rule. So yeah, you can. You can always rewrite it. Okay, so in any case, we now have the first derivative. Then what would we need to do? Now we get to do the second derivative. Yeah, Nate.
For some reason, I'm having trouble just like getting from the chain rule, simplifying it from 2 t squared plus 1 to the negative 2 times t squared to 4t over.
Oh, that part?
Can you just do
Well,
yeah.
The negative 2 and the 2t at the end, these two things aren't with the negative exponent, right? I kind of treat the thing with the negative exponent as quite separate, because I know that that's already in the denominator.
Oh,
That thing's in the denominator, and therefore these two things are in the
yeah.
numerator. So these two snap together to become negative 14, and then the rest goes down into the denominator. Yeah, good question, Nate. Okay, well, so now to do the derivative again, I think now you just want to do the quotient rule. Because otherwise, if you wrote this as a product with the chain rule, I think that would actually be longer. So now we do the second derivative, and what's the second derivative? It would be ho d high minus high, oh, d ho. So you do have to do the chain rule of the denominator anyway, because you're taking the derivative of the denominator, and the denominator is a chain rule because you've got the outside function and the inside function. So the derivative of that denominator, so that'd be 2 t squared plus 1 to the first times the derivative of the inside, which is 2t. And all of that was just the numerator, wasn't it? All of that was just the numerator. All over ho ho, which is t squared plus 1 to the 4th power now. In other words, this is a long problem. In other words, the calculation is much more in depth than just the calculation using a quadratic or a cubic or a quartic. So how does all that clean up? We have negative 4 times t squared plus 1 squared, and then minus a negative 4t, so that's really plus. Boy, all of that gets multiplied together. I'm going to multiply the 4t times the 2 times the 2t. So that's 4 times 2 is 8 times 2 is 16 t squared times t squared plus 1. And that's all over t squared plus 1 to the 4th. Now this is really exciting right here, folks. What can we cancel from the top and bottom now? Yeah, you can cancel 1 t squared plus 1. You've got t squared plus 1 squared here. You've got a t squared plus 1 to the first here. And you've got t squared plus 1 to the 4th here. So you could remove 1 t squared plus 1 from all of those. Which is nice because then it cancels one of those. It cancels this whole one and turns this into a 3. So now we have the second derivative, which is negative 4 t squared plus 1 plus 16 t squared all over t squared plus 1 cubed. And then what else can you do? What can you do with that numerator?
Take that a 4.
Yeah, we could distribute the 4 now into the t squared plus 1, stop viewing it as a t squared plus 1 binomial and simply distribute it, because then you have minus 4t squared minus 4 plus 16t squared, and now you have like terms, and you can combine like terms in the numerator, and you end up with 12t squared minus 4 all over t squared plus 1 cubed. Wow! Look at that final answer, folks. This calculus is a great example of how things have to get worse before they get better. Have you ever heard that phrase? Things have to get worse before they get better? Well, the middle of that quotient rule was looking pretty bad. And yet finally it resolved itself into something that's not that bad at all. So here's our first derivative now. And there's our second derivative. And then you would go about doing the actual problem. So we had to spend a good deal of time taking the first derivative, then the second derivative, but now you'd go back into the curve sketching routine and find the critical points, plug those critical points into the second derivative to find out if they're concave up or concave down, and then plug those back into the original function to find out how high the maximums are and how low the minimums are. Should we finish this problem or move on to the math AS
For
question?
the second step,
Yeah.
let you take off 3
Why did I what?
on the above. Like little bit down here, down, down, down. Yeah, let you take off 3.
That was a 2.
Oh, okay.
Because there were 2 t squared plus 1s there, 1 t squared plus 1 there, and 4 t squared plus 1s there. So I removed a t squared plus 1 from all.
Okay, thank you.
Okay. What do you think, folks? Should we finish this one or move on? I think maybe move on. Well, I don't know. I mean, what do the rest of you say?
All we get to do is just substitute from now. So
Yeah, from here on, you're just substituting into these things to find out if they're positive or negative. Well, actually, no. I mean, there is something that we still have to do. Don't we still have to find the critical points? That means we have to set this equal to 0. Well, when is that going to equal 0? When is, because remember, that's our very first step, is set the first derivative equal to 0. When is negative 4t over t squared plus 1 squared going to equal 0? Do you remember, how do we solve a rational function? How do we say when it's going to equal 0? What do we have to set equal to 0? The whole thing, or the numerator, or the denominator? Well, if the denominator is 0, then we're dividing by 0, and that's a whole or an asymptote. But if we want this whole fraction to equal 0, what has to be 0? The numerator. It's only the numerator has to be 0 in order for this thing to be 0. And therefore, when will negative 4t equal 0? Just when t equals 0. There's only one critical point, and it's t equals 0. Now, hold on. There's only one critical point when the derivative is equal to 0, and that would be t equals 0. Because negative 4t will only equal 0 if t equals 0. But that's only if we set the first derivative equal to 0. What else do you have to set the first derivative equal to? Undefined. Because your critical points are anytime the first derivative is 0 or undefined. Will this thing ever be undefined? That is, will we ever divide by 0? Look at this thing, t squared plus 1 squared. First of all, anytime you square anything, the number becomes positive, right? So we're always dividing by a positive number. Well, could this ever be 0? Because what's the smallest t squared itself has to be positive or 0. So if it's positive, positive plus 1 is positive, which squared is still positive, so it's not 0. But if I let t equal 0, then 0 plus 1 is 1, and 1 squared is 1. So can the denominator ever be 0? No, great. So this will never be undefined, and therefore there's only one critical point we even have to think about. Wasn't that anticlimactic? We did all that work, and there's only one critical point. And it's in the middle. My goodness. So what is that critical point? Is it a max or a min? Let's go ahead and plug it into our second derivative. We can't help ourselves. Let's finish this problem. So what do I do now? Now that I know my critical value is t equals 0, I plug it into the second derivative. Maybe we can calculate this in our head almost. What happens if I plug 0 into this? That's 0 minus 4, which is -4. And then 0 plus 1 is 1, and 1 cubed is 1. And therefore, it's negative. So what does that mean our critical value is? Concave down? So it's a maximum. So there's a maximum at t equals 0. And how high is that maximum? Now what do? We plug it into the original. So I plug 0 in for t. 0 squared is 0 plus 1 is 1. And the highest point there is 2. So on this graph, all we know for sure is that when x equals 0, the height is 2, and that's our maximum. And that's all we found out. That's all we found out. From all that work of doing the first derivative, the second derivative, there was only one critical point, and we know there's a maximum right there. I bet there's something that you all want right now, other than chocolate. You want to graph it and see what it looks like, don't you? You want this gratification of knowing, is there really a maximum there? Do you all see it? Is that exactly what we predicted? Is there only one critical point? Sure enough. That's it. Now, compare the graph to our curve sketch graph. Pretty close, right? I mean, other than the fact that we had no idea what was happening to the right or to the left, you know, we nailed it. Is anybody impressed by this? Maybe not. I don't know. I mean, it's pretty impressive if you take that perspective that this mathematics agrees with what the graphing calculator told us. Okay. Well, let's move on, folks. Let's go look at section 2.8 in the Math AS. Now, let me ask you. I mean, obviously, what I'd like to do is petition the school to make this class longer. You know, from an hour 50, maybe we could push it to 2.5 hours, maybe 3 or 4 hours. What do you guys think?
No,
Have a lunch break in the middle? No?
No,
I could definitely spend more time in here with you guys. I'm always sad when class ends.
but I don't want to.
You don't want to? Jeez, Carmen, thanks for your honesty. Tell me how you really feel. So part of me wonders, should we focus on doing the Math AS first and then doing the book? Because lately I've been doing the book first as kind of lessons, and then we just turn our attention to Math AS. And I figure that's like a bonus. I'm like helping you with your homework. But does anyone feel like we should do the Math AS first and then do the book?
Yeah.
And why is that? No, go ahead, Nate.
I feel like we see more of these problems throughout with the homework and then on the quiz and test. I feel like we see more similar problems.
To what, Math AS?
Yeah, than the ones we see in the book. Sometimes it's hard to like translate like the sections we do in the book to apply to quizzes and homework and stuff.
Well, that's
Some
fair.
of the videos Math AS shows is they're like somewhat awkward.
Awkward.
They're just
Yeah.
weird. It
Like
was
people
talking
dressed
about,
up in duck
it
costumes?
was talking about sins and cons and all that stuff, which we don't do here.
Civ?
Sin, S-I-N.
Sign.
Oh, sine and cosines.
Sine and
Oh, okay, I got you. Okay, well, folks, then that's fine with me. How about we'll start normally with the 2.8. We'll start with the Math AS next time forevermore. We'll do Math AS first, and then maybe I'll just choose a couple problems from the book. But here's the thing, the book is, I consider the book important. I've been reading the book. I mean, I read the book before I come to class. I do the examples in the book because that's how I know what they want me to be sharing with you. Okay, well, in any case, let's go ahead and go. No, stay where you are. Don't move. I mean, let's go ahead and start Math AS. So we won't have to do every single one of these problems because some of them I think we've seen. Like number 1, haven't we seen this problem before? Okay, I'm just going to skip it then. Because they're just asking us to identify what is true about that point. So I'm just going to skip it. Oops. So number 2. Oh, I feel like we've seen number 2 as well. And you can't even read it. It says, for this function, there are 3 important open intervals where a and b are critical numbers. Find a, find b, and then for all those intervals, say whether it's increasing or decreasing. We did a problem like this. In fact, we spent a good deal of time doing a problem like this. So I don't think I'll do this one. Okay. Number 3, we've seen a problem like this as well. I'm not going to do this problem. Boy, we're making great time. Number 4, we've done a problem like this. Should we do one? Let's do one of these, because so far there's been 3 of these. We might as well look at it. So that point right there, folks. Now, folks, you don't know multiple choice. You could sit here and look at the multiple choice. But I'm going to tell you, don't even look at the multiple choice yet. Just notice that they're asking about the first derivative and the second derivative. So I'm just going to come up here and say, what's the first derivative and what's the second derivative? So first of all, what's the first derivative? The slope is positive. So I know the first derivative is positive. Next, what's the concavity? It's concave down, and therefore it's negative. So therefore I know that my f prime should be greater than 0, and my f double prime should be less than 0. So I've already identified the answer. Now I just come down here and find where it is. It's not that one or that one. And f double prime is negative. It's this one. So I would encourage you to always determine the answer on your own before you start going through the multiple choice and trying to determine which of the multiple choice is correct. That's a good strategy for everything. All right. Number 5. These are very interesting problems. What are they telling us in these problems? In number 5, we'll start with number 5. What are they telling us?
That it's negative.
That what is negative?
The derivative.
Yeah, the derivative is negative. So they're telling us that the derivative is negative. So if I'm just going to make a graph of it real quick, I'm going to draw that. The derivative is negative. And what else are they saying about it?
It's decreasing.
They're saying that the derivative is decreasing. That wasn't very obvious. The way they worded this is very awkward. It is very awkward. They're saying the derivative is negative, and it's actually decreasing to become even more negative. So what would that mean if the derivative is already negative, but it's decreasing even more? What does that tell you about the concavity? Wait a minute, that doesn't make any sense. Because then it tells us that it's concave. Oh, they're telling us the derivative is negative, meaning it's down here, and it's negative, and it's concave up. Is that fair? Is that what they're telling us? That's what the derivative is. The derivative is currently negative, it's decreasing, and it's concave up. Is that fair? And so they want to know, what is the original function doing? The fact that the derivative is negative means that the original function is slanted down. Okay, so this is the original, this is the derivative. It was negative, meaning it's down here below the x-axis. It's decreasing, meaning it's going down. And it's concave up. That's what the derivative is doing. So now they're wondering, what's the function doing? Well, the fact that it's negative means it sloped down. Now what else?
Well, it's starting to like.
Well, let's take a look at our options. At the very least, we already know that the function is decreasing. So we can cross out A and D. Right? We know it's that.
It has to be concave down.
Why do you think it's concave down?
Because your derivative function,
I think what you're about to say is correct. It would have to be concave down because the derivative is decreasing.
Yeah.
That means the slope is decreasing even more. The slope is decreasing even more, meaning the slope is decreasing even more. And that's what that would look like. So it's decreasing and it's concave down.
Yeah.
I do believe that's the correct answer. How could we check that, though, to be very sure? We could try graphing it, but there's no function. Yeah, there's no function. Well, in any case, I think that that analysis is correct. Because we know, and it didn't even matter, did it, that this thing happens to be concave up. What matters is that it's negative and it's decreasing. So the slope is negative and the slope is decreasing even more. So that automatically means that it's concave down. And actually, I think that's all there is to it. So you didn't need the information about the concave. Oh, and it even said so. Not all info may be used. Ah, what jerks.
So what information are we not?
You're not using the fact that it's concave up. Yeah. Okay, so now that we've done all that, let's try the second one. This function is positive. I'm going to draw a new one now. They're saying the function is positive. So the actual function is positive. This is the actual function. It's positive, it's decreasing, and it's concave down.
What's the antiderivative?
We're about to do it. So this is the function. And the antiderivative means doing the reverse direction of the derivative. So for instance, let's say that we had x cubed and we wanted to take the derivative. What would we do? We would bring the 3 out front, multiply by the exponent, and subtract 1 from the exponent. And listen to the rules. Multiply by the exponent, subtract 1 from the exponent. Now run that in reverse. Add 1 to the exponent. Right? Isn't that what we would do? You'd add 1 to the exponent and then divide by the exponent. So let's say I wanted to do the antiderivative of x cubed. What would I do? Add 1 to the exponent and then divide by that exponent. And that would be the antiderivative. We haven't done this yet. This is integral calculus. They're just kind of suggesting it on the fly to try to run the derivative process backwards. But for sure, since to do the derivative, you multiply by the exponent and subtract 1, you would add 1 and then divide by the exponent. That's the antiderivative. So they're saying you've got this function, and then they're saying that the antiderivative is what? But keep in mind, they're really just doing the same setup. Here they're describing the derivative, and they're looking at the original function. And here again, they're looking at a function, and they're saying, look at the function before it, the original function. Does that make sense? Like for instance, couldn't we call this one f prime of x? And what's the antiderivative of f prime of x? Let's say that this is f prime of x. This is f double prime of x. And this is f of x. If you go in the antiderivative direction, you're going from f prime back to the original function. So that's what they're saying. They're saying, consider that this one is actually the derivative. And then go backwards to the original function. So we're following the same logic as we did up here. Then what can we know about the original function? If we call this the derivative, what can we say about the original function? So what we know here is that, again, I'm going to translate this. I'm just going to say the derivative is positive, meaning the slope is going up. But the slope is positive, but it's decreasing. So the slope is decreasing over time. And that would be the original function. So I would say, therefore, that it's increasing, but concave down. Folks, I feel like this one got away from us. I think I've lost half of you, would be my guess. And I think this is a very poorly worded question. I don't think it's very exciting. And honestly, I can just tell you, I won't plan on putting this on the test. Can we just be friends? Let's be friends. I've never seen a problem like this before. I want
to know Carmen's idea of being friends.
You what?
So I want to know Carmen's idea.
Carmen's idea of being what?
Friends.
Friends?
Yeah, because like she didn't like the idea of like class.
Oh, yeah, but what does that have to do with Carmen's idea of being friends?
Because she has good ideas.
Oh, okay, I see. Well, my idea is that I'm not going to put this one on the test. Is that okay? I'm completely okay with that. Let's keep going. Okay. In this question, is a little more standard. There's a graph and everything. Over which interval of x values is the derivative positive? Oh my gosh. I mean, this question is just so easy. This is going back to basics. Where is the derivative positive?
-4 to.
Yeah, all of this, right? Over the right-hand side of the graph is a positive derivative. So over the interval from 4 to infinity. Well, that was a refresh. What? Oh yeah, -4, sorry. That was a refreshingly simple question. Over which interval is the derivative negative? Well, that's everywhere over here. Folks, should I be using a bracket on the -4?
No.
No, because we're not including -4. What's the derivative at -4?
0.
0. So we're asking for strictly greater than 0, strictly less than 0. Over the interval from -infinity to infinity, this function is? This is amazingly vague, isn't it? Awesome. This function is awesome. From -infinity to infinity, this function is a parabola. What do you suppose they want us to say? Over the whole interval, the function is? I'm guessing they want us to say concave up. Do you think that that might be what they're wanting us to say? Because is there anything that this function is everywhere? It's not always increasing, it's not always decreasing. So the only thing we can say for sure that this function is always is concave up. Or awesome. Or parabola. How would you make parabola an adjective? You're looking awfully parabola-y today. Or what?
What?
What? Okay. Okay, same thing goes for number 8. Let's skip it. Number 9. Oh. We can look briefly at number 9. This is slightly different. What are they asking for this time? It's not first derivative. They're asking for
When it's concave down.
yeah, when it's concave up or concave down. So when's the changeover point, folks? What's your best guess? Yeah, probably -1. That's the inflection point. So there's an inflection point at x equals -1. And it's concave up over here from -infinity to -1. And it's concave down over there from -1 to infinity. Boy, compared to number 5 and number 6, these problems are refreshing, right? They're just very straightforward. This isn't challenging at all compared to some of the other things we've done. Okay, well, there are a few problems we're not going to get to today. How about number 10?
I think we went through one of these.
Yeah, we did one of these.
We did?
Yeah.
Oh, okay, well, great. Let's move on to number 3. I'm sorry, 11. Oh, good, because number 11 is more of a type of problem that you'll see on the test. Let's do number 11, and then we'll be done for the day. So in number 11, they're telling us that f of x is equal to this chain rule function, right? You've got 3 minus 3x all to the raised to the power of 30. Now, if you wanted to, folks, couldn't you multiply that out? You could take your time, multiply that out using FOIL, and then you would simply have a polynomial. And it'd be much easier to do the derivative. But that takes a lot of time. So instead, you use the chain rule. So they're asking us for the critical values. So that means find the first derivative and set it equal to 0. So what's the first derivative? You have to do the chain rule. 3 minus 3x. So you take the derivative of the outside, leaving the inside alone, and then you multiply by the derivative of the inside, which is just -3. And so now that's -9, 3 minus 3x squared. That's our first derivative. And we would like to know, when is that equal to 0? By the way, a critical point is when the first derivative is 0 or undefined. Will this function ever be undefined? No, why not? Because you're never dividing by 0 and you're never square rooting, so it's never going to be undefined. But it could be 0. So you set it equal to 0. Now we have to solve for x. So x is being multiplied by -3, added by 3 squared, and multiplied by -9. So you divide off the -9. And now you have 3 minus 3x squared equals 0. So again, the whole thing is being squared, so you'd square root both sides. And now you have 3 minus 3x equals 0. And then I'll move my negative 3x over the other side. 3 equals 3x. And so x equals 1. Gosh, I guess we could have figured that out right up front. Because what's the only way for this thing to equal 0? If that minus that is equal to 0. And when is 3 minus 3x ever going to equal 0? If x equals 1. Because then it's 3 minus 3, which is 0. So x equals 1 is the obvious answer, and that's your critical value. A equals 1. That's your critical value. Which, apparently, since it's a cubic, what do you think is happening there?
2.
Would that just be a changeover point? Do you think that's what it is? Just a changeover point? Maybe, because it says there's only one critical value. So if there was a maximum, the curve still has to eventually go up. So if you had a maximum anywhere or a minimum anywhere, you'd have to have 2 of them. So it probably looks like this. And they're saying to the left of A, what's happening? And to the right of A, what's happening? So how do we find out? Put the 1 into the original function? Well, if we put it into the original function, 3 minus 3 is 0, and 0 cubed is 0. So I know that I have a coordinate at 1, 0. So hold on, let's make a better graph.
Don't we have to get the second derivative and set it to 0 so we know if it's positive or negative?
Yeah, we could go ahead and do that. So the second derivative, we have to do the chain rule again, would be, oh boy, negative 18, 3 minus 3x times negative 3 again, which is 3 times 18 is 48 times 3 minus 3x. So that's our second derivative, and we have to plug 1 into that. Well, that's 0. Because again, 3 minus 3 is still 0, and 0 times that would be 0. So the concavity is what? It's not concave up, it's not concave down, it's concave flat, which probably means it's a changeover point. Right? Isn't that one of our possibilities? Yeah. Concave 0 is either flat or a changeover point. So that means this is what our graph looks like. So to the left of our critical value, what is the graph doing? Increasing. And to the right of A, what's the graph doing? Increasing. Boy, that was pretty, they're not even asking very difficult questions about this. But I think that's it. Okay, so next class, folks, we'll start by finishing these because I think 12, 13, and 14, and 15 are a little more tricky. So I'd like to go over it with you. And then next class, we'll start 2.9 with the Math IS problems instead of the book. Nate?
Wait, for that last one, were they both increasing?
I saw that they were both increasing. How could we check? Graph it. What's the question? 3 minus 3x cubed?
Yes.
Oh my gosh. What a silly assumption I made. Was it increasing everywhere? No, it was actually flipped. It was actually decreasing everywhere.
Because it was a negative.
It what?
Was it because it was a negative?
Because it's 3 minus 3x cubed instead of x minus 3 cubed. So I wonder how how mathematically could we have figured that out, that the graph was going like that, not that. We would have had to look at the first derivative to the right or left. We'd have had to look at the first derivative to the right or left. Or we could have looked at the second derivative to the right or left of 1. But the key is we would have had to look to the right or left of 1 to actually find out. So, boy, that was a silly assumption that it went up like that. It was actually going down.
So they're both increasing.
They're both decreasing. Yeah. Oh, folks, I keep forgetting to pass back tests. Is Mong here? Here you go. Is Thomas still here? Here you go.
I forgot to show you my practice status.
Oh, good. Hayden's here right now. Is Nate still here? Nicholas still here? Julie, you're still here. David's going. Nicholas is gone. David's gone. Julie is here. That was your practice test. Where is this going? That's the practice? Okay, yeah. Thank you. Yeah, thank you. See you guys.
Bye.
Bye, Carmen. So, Mong, I would like to have, if you're interested, I would like to sit down and review the test with you. Not right now. It doesn't have to be right now, but at some point, please, can you make time to come to the office and we'll go over it?
Yeah,
Okay, good.
but right now I have one question.
Yes.
Sorry.
So, yeah.